Hi guys, today we're looking at applying de Moivre's theorem to solve for a complex number z which is raised to the power of n, i.e. use de Moivre's theorem to solve for z to the power of n. Your key term in these questions is solving for z. Let's look at an example from exercise 12.10. Use de Moivre's theorem to solve for each of these equations. Let's look at part 3. Solve for z squared is equal to 1 plus root 3 to the root 3i. In these questions, when you're solving for z, the power that you have raised z to is the number of roots that you should find. So in this case, z is raised to the power of 2, and therefore I should have 2 complex numbers as my answer. Step 1. Solve for z. To do this, we square root both sides of the equation. Z is equal to 1 plus root 3i to the power of a half. Step 2. We now write a plus bi in polar form. In this case, we're writing 1 plus root 3i in polar form. To do this, the first thing we need to do is find our modulus. When finding the modulus, a is equal to 1 and b is equal to root 3. Our modulus or is equal to the square root of a squared plus b squared. Substituting our values into our equation for the modulus gives us the square root of 1 squared plus root 3 squared, which leaves us with or a modulus of 2. Remember that the modulus, again, is the distance that a complex number is from the origin, or. We now need to find theta, which is the argument. This is the angle from the positive x-axis to our complex number, measured anti-clockwise. To find our argument, we first find a. A is equal to inverse tan of root 3 over 1. A, our reference angle, is equal to pi over 3. This is the angle for this complex number in the positive x and y quadrant, i.e. in the first quadrant. We now use this value of a to find theta, the argument. Draw up where your complex number is. In this case, our complex number is in our first quadrant, and therefore theta, our argument, is equal to a, our reference angle. Theta is equal to pi over 3. We now take these values and write our complex number in polar form. In polar form, 1 plus root 3i will be written as or times cos of theta plus I sine of theta. Substituting our values in, this gives us our complex number in polar form of 2 times cos pi over 3 plus I sine pi over 3. We now need to write the complex number in general polar form. This is our equation in polar form, which allows us to find the equivalent complex number in any quadrant on our Argand diagram. In general polar form, our complex number is of a plus bi is or times cos of theta plus 2 pi k plus I sine of theta plus 2 pi k. This is similar to the method we use when solving our trigonometric equations. We now substitute in our values to write our complex number in general polar form. This gives us 2 times cos of pi over 3 plus 2 pi k plus I sine pi over 3 plus 2 pi k. Now that we have our complex number written in general polar form, we can apply de Moivre's theorem. It is important in these questions to first write our complex number in general polar form because, as we said at the start, when we're solving for a value of z, you will have more than one answer. In this case, we want to have two roots. Applying de Moivre's theorem to our general polar form gives us 1 plus root 3 to the power of a half will be equal to, or to the power of n, where n is your power, times cos of n times, this is very important, so our n value, our power is times by theta plus 2 pi k, plus I sine n times theta plus 2 pi k, because this whole value in here gives us our angle. Substituting our values into our equation, we get 1 plus root 3 to the power of a half is equal to 2 to the power of a half times cos of 1 half times pi over 3 plus 2 pi k. So again, note that our value of n is multiplied by our whole angle, where our angle is pi over 3 plus 2 pi k. And then finishing this off, plus I sine of a half times pi over 3 plus 2 pi k. Let's simplify this. Multiplying 1 half by our angle gives us 1 half times pi over 3 equals pi over 6. And 1 half times 2 pi k leaves us with pi k. Because this would be 2 pi k times 2, where they cancel out and we're left with pi k. And doing the same if our sine value gives us I sine of 1 half times pi over 3 leaves us with pi over 6, plus 2 pi k times a half gives us pi k. We now find our two solutions of 2 to the power of a half times cos of pi over 6 plus pi k plus I sine pi over 6 plus pi k. To do this, we solve for when k is equal to 0 and when k is equal to 1. If we were solving for more than two solutions, we would continue to substitute in for k is equal to 2 and k is equal to 3, etc. In this case, we're left with 2 to the power of a half times cos of pi over 6 plus pi times 0 plus I sine pi over 6 plus pi times 0. This leaves us with 2 to the power of a half times cos of pi over 6 plus I sine pi over 6. This is our first value for z. If we're asked to write this complex number in rectangular form, we multiply our values back together. Cos of pi over 6 gives us root 3 over 2, and I times sine pi over 6 leaves us with 1 half I. Multiplying this value by 2 to the power of a half, or root 2, leaves us with root 6 over 2 plus root 2 over 2i. This is our first solution for z. Let's find our second solution for z. To do this, we substitute in for k is equal to 1. This leaves us with 2 to the power of a half times cos of pi over 6 plus pi to the power times 1 plus I sine pi over 6 plus pi times 1. Adding together our angles, we're left with 2 to the power of a half times cos of pi over 6 plus pi gives us 7 pi over 6 plus I sine 7 pi over 6. Again, if we're asked to write this in rectangular form, we multiply our modulus by our cos and sine angles. This would give us root 2 times cos of 7 pi over 6 gives us minus root 3 over 2. And sine of pi over 6, 7 pi over 6 times I gives us minus 1/2 I. Multiplying our values by our modulus leaves us with minus root 6 over 2 minus root 2 over 2 times I. Please pause and take down the solution. Let's look at another example. If omega is equal to minus 2 root 3I, solve for the equation z minus omega is equal to 0. The first thing we do here is solve for z. Z to the power of 4 is equal to omega. Therefore, z to the power of 4 is equal to minus 2 root 3I. And z is equal to minus 2 root 3I to the power of a quarter. We now write our complex number minus 2 root 3I in polar form. That's or times cos of theta plus 2k pi plus I sine theta plus 2k pi.